Okay, so for this first one, it says the slope of a curve is given by that formula. So that is our dy dx. And we want to solve the differential equation for this initial condition, -1, 1. So we're going to basically cross multiply over the y cubed, and then multiply over the dx. And then we're going to do the antiderivative. So this will be 1/4 y to the 4th. And then this will be 2/3 x cubed plus c. And then we need to find c, so we're going to plug in our initial condition. So -1 for x, +1 for y. And so that'll give us 1/4 equals -2/3 plus c. And I'm going to need to add the 2/3 over. So our common denominator would be 12ths. This would be 3/12 equals -8/12 plus c. Add that over, and we're going to get that c is 11/12. And so you want to go back to the step right after the antiderivative, recopy that exactly the way it is, except put in your c value. And then we're going to get y by itself. So we're going to multiply over the 4. So it would be 4 times all of this. And then to get rid of the 4, we're going to do a 4th root. Anytime you do an even root, you would want to think about plus or minus. You don't need to worry about it for the odd roots, but for the even roots, think about plus or minus. And it comes from the y value, the output value of your initial condition. This one's positive, so we want the positive 4th root. Right, a particle begins at 2, 1, so that's our initial condition. It is moving. Its velocity, and it says y prime, but we're gonna, do dy dx or dy dt, however you want to say. I guess we'll use t for time in this one. So dy dt is quadruple, so 4 times the position y, so 4y. So we're going to divide over the y, multiply over the dt, and then do the antiderivative. So for the left side, that's ln of y. And then over here, this will be 4t plus c, and we're going to plug in the initial condition. So 2 for x, 1 for y. ln of 1 would be 0 equals 8 plus c, and so c is -8. So again, we're going to go back to the step right after the antiderivative, recopy it exactly the way it is, but put the c value in there. And then we want to get y by itself. So to get rid of the ln, we're going to do e to the power of all of this stuff. When you get rid of an absolute value, you also want to think about positive and negative, and this one would be positive. All right, this one doesn't have an initial condition, so we just skip that step. You don't have to find what c is. So we would divide over the y, multiply over the dx. Antiderivative. And so this will be ln of y equals 1/8 x to the 8th plus c. And then to get rid of the ln, we're going to do e. And to get rid of the absolute value, I'm going to put a plus and minus. It would be e to the power of all of this. E is a number and c is a number. So we write that out front as one great big constant. So it's c e to the power 1/8 x to the 8th. Again, because e is just a value and c, a constant, is just a value, e to the power c would just be a value. And so you see it written that way. It'll just be out front as one big constant. All right, and then this one, we're going to divide over the y squared. I'm going to write it as y to the -2 dy, and then we're going to multiply over the dx. If you want to put a 1 there to remind yourself it's 1 dx, you can do that. If you don't need to, fine. I'm just throwing it out there as a suggestion. So antiderivative, we would raise the power. It would be y to the -1, and then you divide by the negative. So that would be -1 over y. And over here, we'll have x plus c. Plug in the initial condition. So x is 0, y is 2. And so c is 1/2. We're going to recopy this step, but put the -1/2 in there. And then we have to get y by itself. So here's what is going to happen. We're going to multiply over the y and then divide over all of this. So the y, mathematically, that's what's happening, is the y gets multiplied over here, all of this gets divided over, but essentially they're just going to switch places. And so we have 1 over x minus a half equals y. All right, so here we're going to draw the slope field for this differential equation. Everywhere that x is 0, we're going to have a 0 slope. Everywhere that y is 0, we're going to have an undefined slope. So you can go ahead and fill those in. When x is 0 and y is 0, we're going to have 0 over 0. So we're not going to put anything on that point. So we can put 0 slopes for all of these and undefined slopes for all of these. All right, and beyond that, I'm just going to go point by point. We are going to be able to reflect this stuff over here. Over here, x is negative, and over here, x is positive. So we will be able to do some reflecting. So we'll be able to, like, once we knock these out, we'll be able to do like the mirror image over here. All right, so this is -2, 2. So if x is -2 and y is +2, we're going to have -2/4, which would be -1/2. So maybe like something like this. It's not going to be perfect, just in relation to each other, they have to make sense. All right, this one is -2, or I'm sorry, -1, 2. So if x is -1 and y is 2, that would be -1/4, so even less steep. And again, I'm going to take those and just reflect them over here. And I'm not grading your art skills, you know, just do your best. All right, this is -2, 1. So if x is -2 and y is 1, we're going to have -2 over 2, which would be -1. So a little bit more steep than the -1/2. And then -1, 1 will give us -1 over 2, so -1/2. So same as that. All right, and then down here, these are going to just get reflected, right? Because if y is positive up here and negative down here, that's just going to make them opposite. So I'm going to just actually take all of these and reflect them down here. Yeah, that's pretty good. All right, for number 6, a slope field is already drawn. We're going to draw in the solution curves for these initial conditions. So all you have to do is start at that point and then flow along with the slopes. So starting at 0, 1, that would put us right here. We're just going to go along with those slopes. And then for 0, -2, we're going to start right here. And again, just follow along with the pattern. All right, and just make sure you go all the way to the edge of the graph. That's the one thing that they do look for on the AP exam. If you don't make it go all the way to the edge, then they won't give you the points for it. So just make sure it goes all the way to the edge of the graph. All right, number 7 and 8, we're going to need a calculator for these, so make sure you've got your calculator. These are our exponential model problems. So the rate of growth of a certain bacterium is proportional to the number present. That is proportional to the number present. That means it's going to be exponential. So that means this is your formula. There are 500 present initially, so that's going to be C. And then it says there are 800 7 minutes later. So I'm going to put in 800 for the amount, or you could use B for bacteria. I use Y just because that's what I'm used to using. It's not going to make a difference. Equals E to the power K times, what did they say, 7 minutes. So our time is 7. And then we're going to solve for K. That's what we're missing. So divide over the 500. That would be 8/5 equals E to the power 7K. ln both sides. So ln of 8/5 equals 7k, and then divide by 7. And so that is what we are going to put in our calculator. So ln of 8/5 divided by 7. So we get 0.067. And I'm going to store that as A, store alpha A, enter, because I'm going to need it for part B, and you have to copy paste, because if you chop off all this part of your decimal point, then your final answer isn't going to be accurate enough. Now it says write an equation for B. Again, you can write B. I used Y here. It doesn't really make a difference. All right, B equals 500 e to the power 0.067 t. So that is our equation. And this says use that to predict the amount of bacteria at 12 minutes. So we're going to take 12 and plug it in for time. So it's going to be 500 e to the power. Now it says 0.067, but I'm going to do alpha A times 12 is what we're plugging in. So we get 1,119.154 bacteria. All right, and then basically we're just going to practice that again. Radioactive element has a half-life of 50 years, 700 grams present initially. And then I go ahead and tell you what half-life means. So write an equation that represents the amount. We're going to have y equals 700 e to the kt. And we have a half-life of 50 years. So 50 is going to be the time. And then we end up with half of what we started with. So half of 700 would be 350. And the half-life was 50 years. And so we're going to do the same steps as we did up there and just solve for k. So divide over the 700, that's going to give you a half because it was a half-life. And then ln both sides and divide by 50. So that is what we are going to type in our calculator to get k. So ln of a half divided by 50. And we get a negative rate because the amount is decreasing. And I'm going to store that, store alpha A, enter. And it said write an equation for G for the amount. So G equals 700 e to the power negative 0.013 t. And then how many grams remain after 300 years? We're just going to plug 300 in for time. So 700 e to the power, and again, use your stored A value for that to copy paste, times 300, and we get 10.9375 grams. You only really need to do 3 decimal points, but since that only went 1 decimal point further, I just went ahead and moved the whole thing, because why not? All right, and then here are your logistic model problems. The size of a population is modeled by a function P, so P for population. This 1/300 is our K value. The 750 is L, that's your carrying capacity. P is people, time is in years. So what is the carrying capacity? 750 people. So it means, you know, wherever they're living, the population is going to level off around 750 just based on the resources that are there. So what is the size of the population at the moment when it is growing the most rapidly? And so that happens at the inflection point, which is L/2. So it's going to be 750/2, which is 375 people. So the population will be 375 people when it's growing the most quickly. All right, so 10, the growth of a person, so this is like as you gain height throughout your life, follows a model with logistic differential equations. So again, here we've got 0.5 is our K value, 72 is our carrying capacity, H is height, time is in decades, the initial height is 24 inches. So the height for this person will level off at the carrying capacity, so 72 inches. And then we're going to write a model H of T to represent this. So it would be the carrying capacity over 1 plus, what was the initial amount? 24 inches, 24 e to the negative kt. And whoops, I'm sorry, recording this first thing in the morning here, and so I'm like not on my game, mixing it up with the exponential one. We have to find c. So it says initially 24 inches. So when we plug in 0 for time, we will get 24 inches. I'm sorry, mixing it up with the exponential one here. C is the initial amount for exponential, but not for logistic. And we're plugging in 0 for time. So initially 24 inches. So this would just be 0. E to the 0 power would be 1. So you can basically like ignore that part. And then we're going to multiply over the 1 plus c, divide over the 24. So it's like in the other differential equation we were solving where these two are just going to switch places. So we're going to multiply over the 1 plus c, divide over the 24. So we'll get 1 plus c equals 3. And so c is 2. All right, so let me go back and rewrite this and plug in 2 for our c value. All right, so we still need to find k. That's the other unknown. Oh, no, we have k. K is right there, 0.5. Gosh, I'm sorry. All right, so there we have everything. That is our equation. All right, and then what is the inflection point? Find both t and h. Well, h is going to be the carrying capacity over 2. So h is going to be 36 inches. To find t, you would need to plug 36 in for h here and then solve it. So we're going to have 36 equals 72 over all of the rest of this. So again, we're going to multiply all of this over, divide over the 36. So essentially, they're just going to switch places. We'll have 1 plus 2e to the power negative 0.5t equals 72 divided by 36 would just be 2. Subtract over the 1. Divide by 2. And then ln. And divide by the negative 0.5. All right, so let's see what that gives us. ln of a half divided by negative 0.5. And so I got 1.386 and time was in decades. So around 10 years old, or I guess 13 years old, is when this person is growing the most quickly. All right, and then here are our Euler's method problems. So let this function be a solution to this differential equation. Our initial condition is 1.5. So let me start making a chart here. We're starting at 1 for x, 0.5 for y. We want to find the approximation for 1.2. We want 2 steps of size 1/10. So this would be 1.1 and then 1.2. And so whatever lands there is going to be our answer. We're looking for the approximation for 1.2. So whatever we get there is going to be our answer. So this is considered y0. y1, to get the next one, you're going to take what you started with, so the 0.5, plus your step size, which was 0.1, and then times the derivative at that previous point. So we're going to plug in 1 for x, that would give us -2 right there. And then a half for y, that would be 1.5. And then we kind of need to sort through this and see what we get. So 0.5 plus, this is like the tedious part here, 0.1 times -1/2. All right, so that's going to be 0.5 minus 0.05. So that will be 0.45. All right, and then we're going to do that again. So to get the next one, you're going to take what you started with, what the last one was, plus the step size, and then the derivative at this point. I'm going to need to pick up the calculator at this point, or I guess you could just leave it alone, really. You could do, if it was non-calculator and you had a free response, plugging in 1.1 for x, and then plus 3 times 0.45 for y. I guess technically, I'm going to let you guys use a calculator, but technically, if it was free response, you could just leave it like that. Let me type that in and see what I get, though, just for the sake of getting a neater answer here. So I got 0.365 for that. So they do tend to get a little messy with the decimals. The process isn't hard. It's just, if you're not allowed a calculator, it can kind of be a lot. All right, and then for this last one, here's our differential equation. It's in terms of this function g of y, which is given right here. Initial condition is 2,8. So let me get the table set up here. We're starting at 2,8. We want the approximation for 2.5 with step size of 0.25. So this would be 2.25 and then 2.5. So we don't need to go any further than that, which is kind of nice. All right, so again, this is considered y0. To find y1, we're gonna take where we started plus the step size, which was 0.25. I have a feeling this will be better if I write it as a fraction. Let me see how this turns out here. All right, and then times the derivative at that point. So we're plugging in 2 for x, so 2 times 2 would give us 4, minus g of y. So y is 8, g of 8 gives us negative 12. So minus negative 12 would be plus 12. And so we get 8 plus, that would be a 4th times 16, which is 4. And so that'll be 12. So then going to the next one, it's what your last value was plus the step size times the derivative at that previous point. So 2 times 2.25, let's see, that would be 2 1/4 would be 9/4. So doubling that would be 18/4. So what is that, 9/2? Minus g of y. So y is 12, that would give us 4. So let's see what this turns out to be. And I guess, again, technically, if it's free response, you could stop there and just leave it like that. Let's pretend it was like multiple choice and you had to keep going though. All right, so this would be 9/2 minus 8/2. That would be 1/2. So this is 12 plus an 8. So I guess you could leave it as 12 and an 1/8. I'm fine with it, whatever you want to do. I'm going to let you use a calculator anyway. So you could either stop here and just not simplify it down, or you could type it in the calculator. I'm good with either.